is probably, you can put it down, and Dr. Pawan, you may note it and can later put it on before me.
Yes, sir. Yes, sir.
Yeah,
Anybody
so
who have query can put it on chat box. I will ask the question.
Oh yes, that will be better. So let me start our discussion over the resource project. So I'd like to share the PPT. Let me have that. Just wait. Is it visible, Dr. Pawan?
Yes, sir. Yes, sir.
Okay.
It is visual now.
Yeah. So let me start on this particular resource provisioning in fog integrated cloud. As deliberated a bit in the inaugural session, that these IoT is a coming up discipline with a lot of data that is going to be produced by the IoT devices. As Dr. Pawan also told that around 20 billions of devices by 2021 is expected over the cloud. So cloud is going to be heavily loaded in the years to come, and not only the cloud, even the network, the internet also, because the data from the edge devices, that is the end devices, to the cloud has to traverse through the internet. So the internet will also be heavily loaded. So how to deal with these kind of problems? The people all across, the researchers all across are addressing this particular problem. We are also doing in the same direction. So my students and other researchers also are working in this particular area. And as you know that the machine learning also has come up in a big way in the days, last few years. So I'll be just discussing upon how the machine learning can be applied over provisioning the resources of the cloud as well as the fog. So we'll say that for better understanding, I have divided this particular talk into two parts. One is the fog integrated cloud and machine learning. That is to make you understand what is fog, what is cloud, and what is the integration of this fog integrated, what purpose they are going to serve in addressing the Internet of Things devices and the data that is being produced by the IoTs. And we'll be deliberating a bit upon touching upon this machine learning also, what a machine learning is, so that you can better understand the problem, the objective that we are going to address. So the second part will be an intelligent admission control manager using the machine learning approach. So we do have applied a particular classification and clustering techniques of the machine learning that we'll be deliberating upon. So hopefully it will be understandable to all those that are not working in this particular area as well, maybe from some other discipline also. I hope that they will be able to understand this particular talk because it's a very, very, very general kind of a talk that I have produced. So let us come to this part one of the discussion, the fog integrated cloud and machine learning. And we start with the IoTs only, right? What an IoT is. So as you look into this particular picture, a number of devices have been connected through the internet, right? So they are all connected through the internet to the cloud. So you see that in between you have the cloud, the blue color one is the cloud. And the various devices, like if I say it's just a cooking utensil. So even your utensil is on Internet of Things. Your bulb is on Internet of Things. Refrigerator, table lamp, and so on. You'll find that even this aeroplane is already on the internet. And machines, various machines are on the internet. The devices on which you are currently logged in is on the internet. The car that you drive usually will be on the internet. Smart devices are also, smartphone are already there on the internet. So in the days to come, even you see the shoe, your shoe is also on the internet. This is what we foresee with the Internet of Things. So it will not be just the Internet of computing machines or Internet of computers that talk to each other by passing through the communication, by passing the data from one place to another. Rather, a lot of things will be on the internet, right? The things that we can perceive, like your table will be on the internet, your building will be on the internet, and even we go on deliberating that even the human being will be on the internet. So that way it is possible that the human beings, the time they are born, they are imbibed the chip inside the human, child, so that we can enable him to be on the internet. I mean, that is what we perceive. And it has been, the kind of a research is already going on in various academic as well as the industrial organizations. But so far what we perceive is that all the devices, all the things that we can think of will be on the internet, right? This is what exactly the meaning of the Internet of Things is. And this particular term was coined by a scientist known as the Kevin Aston, the MIT-based scientist who coined this term IoT, which is estimated to be born between 2008 and 2009. So this term IoT came sometimes between 2008 and 2009. This is the estimate of the Cisco, a leading network company, which estimates that 2008 and 2009 is the years in which this term IoT was born. By now, you know that the IoT has become so prevalent that even a workshop is being organized on the IoTs, right? The IoT is defined as it is the network of physical objects, devices, vehicles, buildings, and so many other items that are embedded with electronics, because it has to be on the internet. So it has to be embedded with the electronics, the software, the sensors, and of course you require a network connectivity in terms of the internet, we say, right? You require a network connectivity that enables these objects to collect and exchange data. Actually, the objective is to collect the data, process the data, and take some action based on the data, right? This is what the objective of this whole designing is, in order to make the world smarter, because ultimately what we achieve from the IoT is that the things are also becoming intelligent, they are becoming smarter, and they can serve the humanity in a better way. This is what is expected from the IoT, right? And it has been defined this way. Some other definitions make it like internet technology connecting the devices, machines, and tools to the internet using the wireless technologies, right? This is how we perceive the Internet of Things. As was deliberated in the inaugural session itself by Dr. Pawan, that over 10 billion things so far are connected to the internet, but this is expected to grow 20 billion, or sometimes it may even cross 20 billions of devices on the internet. So obviously the load on the internet is going to be heavier. And of course, as you know that the devices that are to be on the internet has to have the IP addresses. So obviously the IP addresses that we started using in the beginning for the IoTs, for the internet, that was the IPv4. Now we have come up with the IPv6 that can address even the billions and billions of devices. So that particular problem in assigning the IP address to the devices are no longer exist, because we will be able to address those things using the IPv6 addressing, right? So we can expect that the number of devices that will be on the internet are going to grow exponentially, right? Unification of technologies. So we can define the IoT by the unification of these technologies, as you can look into the low power embedded systems, because they consume the energy. So we say that the embedded systems, I mean the devices that are embedded with the hardware and software, they should have the low power devices, and a lot of electronics discipline people are working in this particular area. The VLSI, the nanotechnology, the microelectronics technology, etc., are working in devising the low power embedded systems. Of course, another area which supports the IoT is the cloud computing, because most of the data that is being generated by the IoT devices either will be stored on the cloud or will be processed on the cloud. So we say that the cloud computing is another discipline, another technology which enables the IoTs. And thereafter, we do have the big data technologies, the machine learning, and the networking, which passes the data from one place to another. For processing the data, we use the big data management, big data technologies, big data analytics, of course, utilizing the machine learning approach, etc., etc. So this is how we see that, how we perceive the IoTs, right? So it's not only electronics, it is the cloud computing, the software engineering, the big data, machine learning, and a lot when we talk about the Internet of Things. Now, coming to the fog computing, what a fog computing is. Fog computing is defined as a horizontal system level architecture that distributes computing, storage, control, and networking. You see that almost everything, the computing, storage, control, and networking functions are coming closer to the users, closer to the devices where the data is being generated. So it has been experienced that many a times for the real-time analysis or for the real-time data that requires the processing in the real time, probably we spend the time in sending the data and collecting it back from the cloud may overdo the purposes for which we have done the processing. So that is why it was thought about that can we bring the computing closer to the devices that generates the data, and that comes in terms of the fog computing, right? Like we see that the clouds are really farer. I mean the physical clouds that we know that gives you the rain. So the clouds are farer and the fogs are closer to the earth. Similarly, we perceive the computing also in terms of the cloud, which is little far, but fogs are closer to the users, are closer to the devices that are generating the data. So this is how the fog computing was defined. Open Fog Consortium is able to come with this particular definition of the fog computing. We can say that the fog is an extension of the traditional cloud-based computing, right? So whatever we do obtain from the cloud computing, obviously the same is done by the fog computing, but then clouds are more equipped with the capacity in terms of the computing capacity, in terms of the storage, in terms of the memory and processing capacity. So the clouds are heavily equipped with all these, and the fogs are not that heavily. So that is what the difference lies between the fog computing and the cloud computing. So, but otherwise we can say that it's an extension of the traditional cloud-based computing model, where implementations of the architecture can reside in multiple layers. So obviously we talk about the multiple layers, and we will discuss that how we can come up with the multiple layers of the computing, storage, control, and other functions that normally we achieve from the cloud computing, right? Similar is the term known as the edge computing. So edge computing, and in fact, most of the literature write it as edge and fog is the same, but we can differ a bit from the edge and the fog computing in terms that edge are those devices that are actually generating the data, but they are also equipped with the processing capability. So even sometimes the data producing devices, if they have the processing capability, may be limited in their capabilities, sometimes the data can be processed there itself. So that way the edge and fog computing differs. We can see what are the fog devices just a bit hereafter, and then you'll be able to make the difference between the edge and the fog computing. So computing done at or near the source of the data instead of relying on the cloud at one of a dozen data centers to do all the work. So as I said that the fog and the edge computing has come up so that we don't have to, let's say, send the data to the cloud for the processing. And of course, mainly we consider it for the time sensitive data that do not have to traverse from the source to the destination and back with the processing. So the term fog and the edge computing came into effect. It doesn't mean the cloud will disappear. So once the fog and edge comes, probably we can think of that as they are serving the purpose, the cloud will disappear, but it will not happen. It only means that the cloud is coming closer to you in the terms that, of course, not the whole computing is coming, the big storage is coming to you. Rather, it is a transient kind of a storage comes to you, mainly to serve the computing purposes, that too for the time sensitive data, for the time sensitive applications, right? Some of the benefits of the fog and edge that we can perceive is the latency that I already deliberated. Rather than wasting the time from sending the data from one to another, probably we can save it if the data can be processed at the data generation point itself, right? So latency is one of the benefit. Of course, the other benefit goes to the privacy and security as well, because you don't have to disclose the data to the cloud, right? Although many of these cloud computing, the cloud service providers, they come up with the privacy and security mechanism, and they ensure that the data that you are passing to the cloud are privately secured by implying some of the security, many of the security mechanism. But then still there is a possibility of breach. So you see that privacy and security are more so if you don't pass the data on the network, and that is what is done usually with the edge and the fog computing. So privacy and security is the another benefit of the fog and edge computing. And then of course we save the bandwidth. So as we do not pass the data on the internet, network will not be heavily loaded, so we'll be able to save the bandwidth. So these three we can say the coarser benefits of the fog and edge computing, but there are many apart from this, right, that you can look into. Now if you look cloud, fog and edge all together, you'll be able to make the difference this way, that at the edge you have these devices, that we call as the edge devices, right? Like you have the table lamp, you have your smartwatch, you have many other, some circuit board, smartphone, and so many other devices that are at the that are treated as the end devices. Of course, are known as the edge devices. So factually, what is happening by keeping it on the internet, these devices are also equipped with some of the processing capability, and that is where we explore, or where we exploit the processing capabilities of these devices by executing some of the jobs along with some of the data here itself in these devices. Then the next layer or the next level of the devices comes to as the fog nodes. And if you look into these devices, you will find that this is usually the routers, the bridges, and intermediate devices in between the cloud and the edge devices. And as you know, are the base stations, etc., that are helping us to forward our data from one place to another. So if actually these devices are also equipped with the processing capabilities, obviously the main job of these devices are not to execute the job, the user's job, rather to implement some routing functions for forwarding the data from one place to another. But these devices, as they have the processing capabilities, we can use, or we can explore these processing capabilities of these devices in executing some of the application along with the sum of the data. That is what we say, that the processing capabilities of these devices are limited, right? So that is how we define the fog nodes. And then probably we move to the cloud ultimately, that are especially defined and designed for executing the application, storing the data. So they have the big storage, they have the big processing capabilities, and so on. So that is how we define the cloud. So now if you look into this particular pyramid, you will find that the cloud servers, they are the well-equipped servers with huge processing capabilities. So, but limited in numbers, like they are the thousands of service providers. These are millions of devices and edge devices ultimately that we have perceived as the that will help us, or that will be creating the environment of the Internet of Things. They are more in number, so billions of devices connected through the internet, right? So billions of edge devices, millions of fog devices, and maybe thousands of the service provider, or the providing cloud providing services. So this way we define the cloud, fog, and edge all together. Is it clear, or is it understandable? At least one of you can nod so that I understand that the things are reaching to you.
Yes, sir. Everything is fine, sir.
Okay, that's fine. Fantastic. So now, yeah, another picture that we can perceive is that here you have the IoT layer that we called as the edge devices. You will find number of devices, many cars, smartphones, the users, refrigerators, air conditioners, and so many other devices. We call it as the edge devices, and of course they constitute the IoT layer. A label above, we have the fog devices, and we call them as the fog layer, right? And then above all, you have the big servers that are providing you the computing and the storage services. We call them the cloud devices. So now fog integrated cloud is actually the amalgamation of these two layers together. So either your job will be executed somewhere here at the fog level, or your job will be executed somewhere here at the cloud level. And we call them together as the fog integrated cloud. So IoT are factually the physical devices that are generating the data. A huge lot of sensors are deployed along with the devices. Probably they sense the environment, they sense the data. So many kinds of sensors are available nowadays. That too are very cheaper sensors nowadays. And that is how it has become possible to experiment with, let's say, the lot of sensing devices, deploying it in the field that do generate the data. And thereafter, the data generated can be passed to the fog devices for processing purpose, or if not so, then probably we can pass it to the cloud for the processing purposes, right? So this is what the meaning of the fog integrated cloud, and they are in fact going to help us in executing the data or executing the applications on the data that have been generated by the IoT devices, right? So this is how exactly the fog integrated cloud can be perceived. Now coming to the machine learning, the another part of this particular discussion that we would like to make it. What a machine learning is, because we do have applied the machine learning, and it is also a discipline which is growing up very rapidly. So let us see, let us have a bit deliberations upon the machine learning as well, right? So machine learning has been defined by the Tom Mitchell of the CMU this way. He said that it is a computer program is set to learn from experience E. So you see that denoting the experience as E with respect to some class of tasks T and performance measure P. So you see you are executing the task T and getting some performance P, right? But now you see that you have applied the experience also E, right? So this E is very important in machine learning. If it's performance at task T, so this task T, the performance of task T measured by P is improved with the experience E. So experience is exclusive to the machine learning aspect, right? So with the experience, the task, the performance of the task T, which is measured by the P, is improved. That is how the machine learning is defined, right? So this particular definition is by Mitchell, as I already told you. And this very precisely defined what a machine learning is, right? So ultimately, in the machine learning, the performance is to be improved periodically. That is what the main objective of the machine learning. So it learns and improves the performance, as it happens with the human being also. So we eventually learn and improve our performance. What we were 20 years back, we have improved from that. If we are not able to, then probably we are not intelligent. That way we can say. So exactly, the machine also has to imbibe the aspect of the intelligence in the machine, the aspect of the human intelligence in the machine, and that is how we can define the machine learning, right? So this particular definition is very well crafted of the machine learning. So factually, it is a branch of AI, artificial intelligence, concerned with the design and development of algorithms that allow computers to evolve behaviors based on empirical data. So you see that normally we write the algorithm and computer executes the algorithm. You give the input, you get the output. But here it says that machine learning is not just giving the input and taking the output. Rather, the development of algorithms that allow computers to evolve. So evolution is very important. So the computers have to evolve periodically, eventually, generation-wise, the computers has to evolve, right? And evolve its behavior based on the empirical data. So empirical data means the data that you have generated. Probably it can also solve the purpose of improving the methods or improving the computers, its performance. That is how we call it as the learning. The computer is learning, and eventually learning makes the computer intelligent, right? As intelligence requires knowledge, it is necessary for the computers to acquire knowledge. Knowledge here we mean the data, empirical data only, right? So it gets the empirical data and improves its performance. That is how we define the machine learning. So machine learning is programming a computer to optimize a performance criterion using example data or past experience. So this is another way we can define the machine learning. Using the example data are the past experience. So past experience is nothing but the output that the computer has generated for a particular job, for a particular program, for a particular applications, right? This, if you look into this picture, you'll be able to clearly distinguish between the machine learning and the traditional programming. So if you look at the first picture, you'll find the traditional programming is like this. It's a physical device, a computer, that you write the program for the computer. So you give the program, a particular program, and correspondingly you give the input data, and probably you get the output data. This is what the traditional programming is. So program itself does not modify itself here in the computer. Rather, it is a fixed entity which operates on the input data. Machine learning is a bit different. If you look at the machine learning, you'll find the same physical computer is given not only the data and the program, rather is given the output also. That is what we discussed or what we deliberated in the previous definition, right? It's not only the data and the program, even the output is given to the computer. So output is also given, and with using those outputs, the computer evolves itself. And this program is different than this program, right? This is the evolved program. May not be in one generation, maybe in hundreds of generations, the program is evolved. So by the evolution of the program, the computer makes itself intelligent. So that is what we call as the machine learning, right? So this is basically we can say that the computer learns by the output which is generated. So you can say it's a feedback kind of a mechanism, right? For the evolution of the machine. Now, why to learn? The question is why we do have to make the machine learn. You see that we are trying to make the machine intelligent. So in order to make the machine intelligent, we need to imbibe such a things in the machine that it learns. Eventually, the machine, like the human beings, we are born with almost the zero knowledge, but eventually when we grow, we learn so many things from the environment, from the society, from our parents, from our peers, from our friends, and so on. We learn, right? Similarly, by learning, we make ourselves intelligent. The human being also getting intelligent, right? By the learning process. Similarly, the machine has to learn. And as I said for traditional programming, it doesn't require learning, like to calculate the payroll. So if you have to write the program for the payroll, there is nothing to learn. And we don't require to apply the machine learning in the, let's say, the payroll software, right? There is nothing to learn. So there is no need to learn when we are going to write the traditional programs or the fixed program. We don't require the learning aspect. Learning is used when human expertise does not exist. So obviously we say that the machine, or we apply the learning to the machine to find it out, to explore where the human expertise are not available, like navigating on Mars. So obviously we know that the Mars navigation on Mars probably doesn't have the human expertise. We expect that, okay, based on some data on the Mars, probably we send the satellite there, they collect some certain kind of a data. Then we say that, okay, use that particular data in learning what kind of environment there is on the Mars. So human expertise is not available, we apply the machine learning. Humans are unable to explain their expertise. Sometimes the expertise is there, but they are unable to explain their expertise. Right? Like the speech recognition, handwriting recognition, etc., where the machines can, let's say, explore it in a better way than the human being. So humans, of course, they have the expertise, but they are unable to explain their expertise. We apply the machine learning. And of course, for those situations also where the solution changes in time, like routing on a computer network. You see that nowadays we don't have the fixed routing, that it follows the same path always. Rather, depending upon the time, the routing also varies. The path also varies. And even for a single communication, the packets follow the different paths, and that too not the fixed path. That also varies depending upon what the congestion is, how heavily the network, how heavily loaded the network is, and so on. So these are decisions where the machine learning can be applied. The machine can learn, or the routers can learn, right? These routers can be intelligent in passing the data from one place to another. So where the solution changes in time, the machine learning can be applied. solution needs to be adopted to particular cases as well, like the biometrics. For a particular case, it has to be adopted itself. So these are some of the situations where the learning can be applied, not confined to these only. There might be many. Now coming to some broad categories of the machine learning algorithms, I will be just deliberating upon some these 2, 3, 4 classes of the machine learning. Like we say that the supervised learning, unsupervised learning, and of course you do have the semi-supervised also, which has not the fully supervised learning. I'll be just deliberating upon, and then reinforcement learning. So supervised learning is basically used for the prediction, right? Most of the prediction models are based on the supervised learning. So, and they learn depending upon the training that they have been given. The kind of a training their machine has been given, they will be able to learn, and thereafter you pass the data, it will be able to predict. Whatever prediction has to be made, right? This supervised learning can be divided again into, let's say, the classification and the regression. Classification is basically on the discrete labels, discrete values, and the regression is for the real values. I'll be coming up to these discrete labels and the real values, discrete values and the real values. You see that in this kind of a learning, the data that is used for the learning are basically the label data, right? The data that we use for the learning is the label data. Label data means the data has been given another attribute by which we are going to classify the data, and we make the machine to learn using that particular attribute, right? That we call as the label. So in supervised learning, the data are the labeled data. I'll be deliberating again it a bit. In unsupervised learning, normally we go through with the unlabeled data, right? Where the data has not been labeled. And in most of the situation, we find that the data is not the labeled one. Then probably we apply the unsupervised learning. So unsupervised learning is for the unlabeled data or the non-labeled data. And we normally use clustering. So depending upon how the data are related with each other, they form certain type of clusters. And we do apply some clustering techniques in clustering those data. Obviously, the data will be estimated depending upon the probability distribution. So some probability, they do follow certain distribution, certain norms, and depending upon that, we do foresee that what kind of a clustering techniques can be applied on these data. Of course, finding association is also important depending upon the features. So we look into using a particular feature, how the data are closer to each other, how they are associated with each other. So we say that even association also determines the clusters of the data in the unsupervised learning. Obviously, dimensionality is the attribute. Dimension is the attribute of the data. So how many attributes are there and how many attributes will suffice to make the cluster is important. Not so many attributes we do have to take into consideration. So obviously we remove the dimensionality, or we reduce the dimensionality of the data sets, right? So this is what usually done in the unsupervised learning. Then thereafter we do have the semi-supervised learning, which is a kind of a supervised learning, but we don't have the labeled data. So what we do, we label some of the data, maybe using human beings or using some method. We label the data, and using those labeled data, we train the machine. So some of the data has been labeled, and the rest of the data are unlabeled. So this is how we define or design the semi-supervised learning techniques. Then the third or the fourth category is the reinforcement learning, which is basically based on the approach where certain task is performed and the reward is given to in performing that particular task. So reinforcement learning is basically based on the rewards that is given to the machine, that is given to the object that are performing the learning process. I'll be deliberating upon this little later. Just exploring a bit more the supervised learning. It is a learning from the past information. So as we say past information, this information has already, the data of this particular information has already been labeled. We call it as the experience. Past information is the experience. So we learn from the experience. Like segregating the images by the shape or color. So this shape or color is actually the labeling of the data. By shape, like we do have the round shape data or we do have the triangular shape. I mean, if you see the image as the data, so images may be round shaped or image may be triangular shaped or maybe some other shape also like rectangular shape or so on, so on. So the data that are coming up can be, I mean, the machine can be trained with this is the round shape data and can be trained with the round shape data, with the triangular shape data. And thereafter, when the input is given to the machine, it will be able to segregate the images by their shapes, like if it is round shaped or the triangular shaped or any other shape. Similarly, by the color also, whether it is a green color, blue color, red color, or so other colors. So the machine will be trained with this is the green color, this is the blue color, and so on, and the machine will be able to learn that particular based on the data. It will be able to learn, and thereafter will be able to segregate the images. Basic input or experience is in form of the training data. So the data using the training data, the machine is trained. So this training data actually forms the domain of the experience that the machine uses. So they form the input as the training data for the machine to learn. Training data are images with tag and label. This is like the round shape, triangular shape. These are the labels that are attached with the data. So data is already attached with the labels, and based on that particular label, we train the machine. And as I already told you, two types of data is possible. Either it is a discrete labels, 1, 2, 3, 4, or so on, or maybe the real values like 2.5, 3.6, and so on. So based on that, we categorize it into the classification problem or the regression problem. And normally we predict, once the training is done, we will be able to predict what type of input will be or what type of data is coming up for the future and that is how the supervised learning is basically used for the prediction purposes, right? If you look into this particular picture, can define the supervised learning like this. Here the learning is being performed on the labeled data, and then after the learning we are able to generate a prediction model. And once we are able to generate the prediction model, we can apply it on some test data which can predict whether it is correct or not. So depending upon how better the training is, the prediction accuracy can be tested, right? This is what the supervised regression, as we discussed. Regression is using the method known as the least square, which is basically of the linear form y is equal to a plus bx kind of a thing, whether x is the predictor variable which is being used in prediction and y is the target variable which is being predicted, right? So these kind of a linear model can be used for the prediction purposes, and obviously the fitting can be done. Some examples where the regression can be applied is the retail forecasting. What will be the retail value that can be predicted? The sales prediction. What will be the prediction of the commodities in the years to come, in the weeks to come, in the months to come? So these kind of a prediction can be made using the regression methods. Then obviously the real estate prediction also. What will be the price of the real estate in the months to come, in the weeks to come, and so on. Weather forecasting is also one. So this, you see that all these are the regression problems because they use the real values, not the discrete values. So once you use the discrete values, they are actually the classification problem. Some standard supervised algorithm which normally are used, but it's not limited to this only. There are many. Some which we have used in our model that I'm going to deliberate is the nav-based method, decision tree classifier, the k nearest neighbor, linear regression, logistic regression, support vector machine, and so many others. Supervised algorithm. And as we discussed, some examples can be predicting result of a game, predicting if a tumor, if a cell is malign or benign cell. That also can be predicted once we are able to train the machine, right? Whether a tumor is malign or the tumor is benign, which is basically used in the health domain, health prediction. Predicting the price of the real estate, stock market, etc. Classifying the emails, whether it is a spam mail or it's a non-spam mail. So all these, at all these places, right? Here you see that the supervised learning is applied. Like either it will be spam or it will be a non-spam. So it's a 0-1 game kind of a thing. So you see that here we are applying the classification algorithm, and real estate prediction, the stock market prediction, etc., are actually the regression problems. When predicting categorical or the nominal variable, it is classification. When real value prediction is made, it is a regression problem, right? Now we move to the unsupervised learning. Learning, what normally happens, basically not always you have the labeled data available for the purpose. Many times it happens that we do have the unlabeled data, no labeling has been attached with the data for the training purposes, right? So no prediction is done here. Rather, what we do in the unsupervised learning, we make the grouping of the similar instances, call it a cluster, and that is what we say, we apply the clustering approach in the unsupervised learning, right? Grouping the similar instances that are known as the pattern. So we observe the pattern. We observe the pattern in the data, and then depending upon the pattern, we can group the similar kind of a pattern, similar instances of the data in a group, in one group, and this way we can have multiple groups of the data, right? Depending upon the pattern, the kind of a pattern that we can have. This approach is known as the clustering approach. So basically in the unsupervised learning, we do apply the clustering approach. Also referred as the pattern or knowledge discovery, right? This particular problem, we call it the knowledge or the pattern discovery. Similarity with basically what we use for the, let's say, identifying the similar instances are the distance measures or some association analysis. These kind of measures are used for testing the similarity of the data. The distance measure, we can use the Euclidean distance method in testing how far the data, one data is from the other data. And depending upon some distance measure, they can be grouped together, they can be clustered together. So this way, the distance measure is used, or sometimes the association. Like if it happens, then this happens, kind of a things. So then these two events can be close to each other. They can be put into the same cluster also. So association analysis is also done, and based on that, probably we do the clustering. Some example applications of the unsupervised learning is the customer segmentation in the customer relations management. This can be applied. I mean, the unsupervised learning can be applied. For the image processing also, we do apply like color quantization, compression, and obviously for the bioinformatics also, we do apply the unsupervised learning. Here you see that the picture is a bit different. Here you don't have the labeled data, rather these are the unlabeled data. They have not been labeled so far. So unsupervised learning model, what actually does, it just takes the data and then applies some similarity measures, and based on that similarity measure, it is able to segregate the data into multiple clusters. Like it will be able to make the rectangular shape object, the circular object, elliptical object, or even the triangular object that are available with the data set. So many clusters can be made depending upon their similarity, right? Depending upon the similarity. If you use some other measure, like segregating the data. If you use the color, you can segregate the data based on the color. If you look at this particular record, the data, apply some clustering approach here. Here we have, let's say, applied the natural language processing based on some semantics, etc. That how the data can be clustered. We'll be able to cluster the data into different clusters like that. This is what the meaning of the unsupervised learning. Some popularly are used standard supervised algorithms are the K-means. K-means most often used. Then the principal component analysis is also very popular unsupervised learning mechanism. The self-organizing map, priori algorithm, DB scan, these are some of the algorithms which is used for the unsupervised learning. For semi-supervised learning, as I discussed, we do have a small amount of labeled data. So we don't have the labeled data, just a small amount of labeled data is there. So we train the machine with using that particular labeled data. Rest of the data is unlabeled data. So maybe 20% data is labeled. Even if the data is not labeled, sometimes we label the data. The acquisition of labeled data often requires the skilled human agent. So maybe we can use the human agent to label the data, right? Or we can perform some physical experiment to label the data. Like we can perform some experiment to determine whether there is a oil at a particular location or not. And once you are able to get that particular data, probably we can train the machine using that particular data. And thereafter, we do not have to perform this kind of a physical experiment, which is usually more costly at some other location. Rather, we can just using the data there itself, using some unlabeled data, we probably can predict whether the oil refinery or oil well is available there or not. So we can label the data, some of the data, maybe 20 to 30% data can be labeled using some of these methods, and the machine can be trained using that particular labeled data. And thereafter, once the training is done, then all unlabeled data can be passed on to that and some sort of a prediction can be made there. So this is a mechanism which we usually call as the semi-supervised learning. The cost associated with labeling makes a fully labeled training set infeasible. So why we are not able to fully label the entire amount of data? Because the cost associated is infeasible. Whereas acquisition of unlabeled data is relatively inexpensive. So this is why we normally label only some part of the data and do apply the semi-supervised learning, right? Of course, an example can be taken here like this in the semi-supervised learning is that teacher provides a set of unsolved problems. Some of the problems he solves in the class itself. Let's say out of an entire exercise, he solves 2 problems and then says that, okay, you do these problems here in the classroom itself. So if it is so, then this is the kind of a semi-supervised learning which is known as the inductive settings. So some of the examples are solved. So some labeling has been defined and rest of the exercise he or she asked you to do so in the class itself. So kind of an inductive setting. In transductive setting, what he says that, okay, 2 problems I have solved, rest of the problem you take it as the take-home exam, right? So you take it as your take-home exam and go in your house and solve the problem. So this is a kind of a transductive semi-supervised learning. So this way we can define the semi-supervised learning by taking this particular example. I hope you are able to make it out. So you see that not the whole exercise is being solved. Rather, some set of problems, maybe 2 problems, 3 problems, a teacher is solving in the classroom, right? Some semi-supervised algorithms are self-training, some generative methods, graph-based method, co-training, even SVM is also used for semi-supervised. And obviously, there are many others. Probably those who are interested in machine learning go through all these, browse through these algorithms of the semi-supervised learning. Then comes the reinforcement learning. So as we discussed, that reinforcement learning is based on the action, and then depending upon the action, a person is rewarded. So reward may be in terms of penalty also. So if you see that if you do good action, probably you can be rewarded. If you do bad action, you may be punished also. So then depending upon the reward and the punishment, the positive and negative reward, normally they call it in the reinforcement learning, makes you to learn the things. This kind of a learning is known as the reinforcement learning. How good is a state is actually the utility estimation. We define the utility, and depending upon if the reward is positive, we say that it's a good state. If the reward is negative, it means we do have to improve on that particular part. Like you can take the example of a child. So when the child maybe starts walking, he may fall down sometimes. Sometimes he may be able to walk 2-3 steps or so. So when he walks 2-3-4 steps, then probably you clap and give them the reward. So clapping is the reward for the child maybe. Sometimes you may go ahead and can give him chocolate also, right? So you see that you are rewarding the child. You are addressing the child. Okay, you have done good job, so you are being rewarded. So the child will be inspired to do or to learn this way. This is the kind of a reinforcement learning with positive and negative. So if the child is not able to walk, sometimes, of course, we say that we should not be discouraged. But sometimes you may say, that, no, you don't do like this. So it is a kind of a negative reward that you do, right? So this is what the reinforcement learning is. And normally we apply the reinforcement learning in game playing, heavily used in game playing, in robot movement, etc. This kind of a reinforcement learning is applied. If you look at this particular picture, you will find what this reinforcement learning is. So this agent makes the actions, and depending upon the action, it is rewarded. Observation is fed back to the agent, and a reward is made to the agent. So this way, the reinforcement learning can be perceived. One example is the self-driving car that has to take many decisions. So you see that the car is driverless, so the car has to learn how to drive, and the machine which is installed inside the car, the computer that has been installed inside the car, they have to take action depending upon so many conditions, like what is the traffic condition, what is the road condition, what is the weather condition, and it has to take certain action, like whether to accelerate or de-accelerate, whether to turn left, right, and so on. So many actions it has to perform. So actions, the conditions, then depending upon that actions, and based on that some reward is made, right? Some reinforcement learning is the Q learning and the SARSA algorithm, which is used normally for the reinforcement learning. So this is the part one. I hope that I'm able to take almost 1 hour of time of yours for the part one itself, but I hope that you understood it. I'll finish this particular part maybe in another half an hour. Is it okay to you? So I'll take a pause, and you also can take a pause so that I can start with the fresh.
Yeah.
Or if you have some question in between on these, probably we can take it on. Hello.
Yes, sir. Yes, sir.
So should I proceed?
Yes, sir. You can proceed, or if you want to take rest for 1 or 2 minutes, then you can take.
No, I already took. I took a sip of the water, and I can proceed hereafter. Okay. So let us come to our problem where in the resource provisioning we do have applied the machine learning. So what we perceive, we started with the Internet of Things, and actually the Internet of Things or even the related devices, they produce a huge amount of data in the volume, in the variety, in the velocity. So the first job is to pre-process these data, because not necessarily the data, the entire amount of data which has been generated by the IoT is valuable to us. So depending upon the property of that particular data, we can do some sort of a pre-processing to filter the data, to cure the data. There are so many terms which is used in the big data, right? So we do have to pre-process that particular data. Cloud not only helps in the data analysis, but also provides storage to these data. So a lot of data is being generated. We do have to preserve that data, and cloud normally helps in this particular aspect. So it helps in the data analysis as well as in the storage of the data. What the problem with the cloud is that for time critical applications, by the time data is sent back and forth to the cloud for the analysis, what happens? The opportunity to act upon may get over. So let's say for time sense, let's say some health application, the data has been generated by the device which are installed inside the elderly person, which generates some sort of data like blood pressure, like blood sugar level, the pulse rate, etc., which is being generated by these devices, the IoT devices. We send these data for the analysis purpose to the cloud. Maybe the time it takes in going to the cloud and coming back after the analysis, maybe the person is critically ill, or sometimes some eventuality may happen with the person. So what has been thought of, so for many time critical applications, it is not advisable to send the data to the cloud for the processing purpose. So we do have to we are looking for the processing somewhere closer to the devices where the data has been generated. And that is what we say. As these devices, we already have discussed, the fog devices probably can serve this purpose better, but the fog devices are limited in the capacity. So you see that not the entire data, entire amount of data can be processed at the fog, rather some sort of data, some amount of data, usually for the time critical applications, can be processed at the fog devices or maybe at the edge devices, right? So fog computing may overcome this limitation by provisioning the time sensitive and priority based. So these two attributes are very important in, let's say, deciding whether the data, the application will be executed in the fog, at the fog devices, or should be sent to the cloud. So these, depending upon the time sensitiveness of the job, the time sensitiveness of the application, and the priority, we can distribute the computation bandwidth and the storage, right? The adoption of such fog integrated cloud. So you see that you cannot isolate the cloud altogether. Rather, you can work in, let's say, complementation with the cloud devices. So we call this altogether as the fog integrated cloud devices. So the adoption of such fog integrated cloud architecture introduces new resource management challenges. So as we do have worked a lot upon the cloud management, cloud resource provisioning, and so on, but now we are looking into the fog integrated cloud architecture altogether and managing the issues that may arise due to the amalgamation of the fog and cloud together, and devising the resource management policies, because once the fog is integrated, then obviously many resource provisioning challenges will also grow up. So how to meet out these challenges, which require introducing a new job scheduling policy with the desired quality of service and the quality of experience. And that is what led to in designing this particular problem. So what we did, an intelligent admission control manager has been proposed for placing the jobs based on the parameters such as CPU, memory, and storage requirement, which normally happens. How much CPU is warranted for doing this, for processing this particular job, how much memory is required, storage is required, besides other categorical parameters like priority, the time sensitivity of the request. That is what, these two are the categorical parameters. The CPU, memory, and storage are the numerical parameters that normally we give in provisioning the virtual machines of the cloud, etc. But this, apart from the CPU, memory, and the storage, two categorical parameters also to be included in the taking the decision of processing the request, which is the priority and the time sensitivity of the request. So what we have done in proposing an intelligent admission control manager is that we do have included not only these 5 parameters altogether. So these last two parameters are basically based on the kind of a natural language processing, that how the priority and the time sensitivity can be included. The proposed work applies kind of a hybrid approach. That is, it applies the clustering as well as the classification. What for we did clustering is to group the resource pool and label the jobs for the training. So first we applied the clustering approach because we are not sure about the kind of a data which is being generated, the kind of applications which is being generated. So what we did, we applied the clustering approach to group the resource pool. It is able to group the resource pool also. What we thought of, depending upon the data, I'll show you some of the result, depending upon which the grouping of the resources have been done. So clustering is done to group the resource pool. Resource pool are actually of the fog integrated cloud. Whether the fog can be grouped in one or can be grouped in many. Similarly, the cloud. So depending upon that, we do have grouped the resource pool. And for grouping, we applied the clustering approach. And with that particular grouping, we are not only able to group the resource pool, rather we are able to label the jobs also. So some of the jobs, we were able to label that particular job. And this job with the label was useful in training the classifier, right? In training the classifier that we eventually applied. So first we applied the clustering, thereafter the classification. So classification of the job is done, for the jobs is done into these 3 categories, 3 classes of the resource pools, which have been devised using the clustering approach. The methodology is demonstrated in terms of the efficiency, which is very important, because the method that we are proposing has to be executed. The method itself has to be executed on the fog nodes. So the efficiency of the method was very important. So the methodology has been demonstrated in terms of the efficiency, the timely execution, the accuracy, how accurate we were in demonstrating this method which we have proposed, and of course the robustness also. So robustness of the method can be tested by introducing some noise. So we do have introduced some noise levels also with the problem, with the data. Some noise is also added while testing our classifier. So that also we do have done this. And of course we devise the multiple size of the batches of the jobs, not a single size batch. Rather, we do have performed the experimentation on the multiple size batches. That I will deliberate. The motivation of this particular problem comes from the job classification is crucial for efficient resource provisioning due to diverse fog and cloud resources. So as we already have deliberated, fog resources are limited in capacity, limited in computing capacity, limited in storage, limited in memory, and so on. Clouds are more heavily, let's say, equipped with these computing resource, computing memory and storage, etc., etc. Right. So it is essential to classify the jobs. What will go to the fog and what will go to the cloud and like that. With precise classification, the mapping of tasks request with available computing resources results in optimal provisioning. That you will come to know. Moreover, to cope with the specific features of fog integrated cloud, use of efficient classification algorithm was essential. So we applied a classification with a little variant in that particular one to suit it with the problem in hand. We do have devised that particular, we do have used that particular classification algorithm. I'll be placing before you very soon. The placement technique in particular must be light and efficient enough. So as I told you, the efficiency of the method that we have devised, the technique that we have devised is also very important. It should be light because it has to be executed on the fog node. So whatever the job request is generated, it goes to the fog node first. So we'll say that the fog node has to take the decision where to forward that particular request. So that is why the placement technique that we have devised or that we have developed should be the efficient and the light enough. And this is one of the, let's say, the beauty of the model that we have developed. The highlights can be pointed out this way, that the grouping the physical request parameter using clustering for effective computing groups that I already told you, and use the standard technique to convert unlabeled data into labeled one. For that also we do have used a technique I'll be putting before you. Proposed intelligence and admission control manager to act on IoT request in a time critical manner. Quick analysis of request parameter including time sensitivity and priority of the job, the applications. To process time sensitive jobs onto the nearest node instead of sending it to the cloud to avoid the network delay. And of course the quality of service degradation. As we already deliberated, these two may cause some degradation in the performance. So to avoid that, we do have devised a mechanism that what can be processed closer to the data generation point. For further intensive analysis, data is forwarded to the cloud as the cloud is strong enough, having the big infrastructure that caters with the volume, variety, and veracity of the data. For clustering, we applied the k-means clustering here. So for clustering, the first phase of our model is basically the clustering in which we are able to cluster the nodes of the fog integrated cloud. So for that, we applied k-means clustering. And using that, we are able to decide not only the clusters, we are able to decide even we are able to label the data also. Okay, this particular, label the job also. This particular job, this kind of a job goes to this cluster or goes to this cluster or goes to some other cluster and so on. So we use the elbow method of the k-means clustering to deciding upon the number of clusters. And factually, this method looks as the total within cluster sum of a square function. So that is usually called as the WSS function. If you are more interested, you can look into this kind of a function of the number of clusters. One should choose the number of clusters. I mean, the WSS is chosen in such a way that such that adding another cluster to it doesn't improve total WSS. So this is the way the WSS is applied. WSS is chosen. For classification, of course, we tested it with many algorithms, but we have applied the decision tree with a little variant of the decision tree algorithm. So decision tree was not only lightweighted, it was able to solve this particular problem of classifying the job into various clusters, various classes where the application is executed. Obviously, we have tested it on the nav based, the linear regression, obviously the logistic regression also along with that. We do have applied the deep learning and AI also, artificial ANN also. But actually it was a bit loaded, so that didn't solve the purpose. We applied the support vector machine with the fast large margin also. Then decision tree, obviously this was the suggestion, this was the problem, this was the model that we do have proposed. We applied the random forest and the GBT also for the classification purposes. The workload on which we do have tested our problem or tested our model is the Google Trace, and the Google Trace has given a lot of data, but those data usually are the obfuscating data. So we do have to cure that particular data, and that we were able to cure the data to solve the purpose that for which we are going to test that on our problem. So we use the Google cluster trace that contains the data in GBs of almost 12,500 nodes for 29 days. So 29 days data we do have taken into consideration. And the trace consists of over 25 million tasks belonging to approximately 930 users. 3 batches of jobs of different sizes we do have devised, as I already mentioned you. We have tested it for batch 1, which is consisting of the 300 requests, the batch 2 consisting of 1000 requests, and the batch 3 consisting of 3500 requests. And this suffices the purposes. That is how robust the machine, how robust the model is. That suffices the purpose in dividing the job into various batches. The framework of the methodology of the work that we do have, if you look into these particular picture, you will be able to make it out. So you see that here you have the end devices that are generating the data, and factually all the data is passed to the nearest fog node, which is this one, let's say, in this particular picture. And here the model resides, here the algorithm is executed. The resource management or the resource provisioning is done here itself, and is decided where the job is to be executed here, or the job is to be given to the some other cluster or some other group of fog nodes known as the aggregated fog node. So aggregated fog nodes are not exactly the same fog node as you do have here in the nearest fog node. I'll be able to make out the difference also between these two. So let's say if the job is to be executed here, immediately the job will be executed and the action will be given, the taken at the end devices. If not so, then obviously we give it to the aggregated fog node, depending upon how time sensitive or what is the priority of the application that are to be executed. And by default, if it is not, then probably it can be given to the cloud for the, let's say, for big data analytics, for making the lifelong kind of analysis, or from historical analysis, which probably has to be equipped with some historical data also. So send for the analysis with the historical data here to the cloud. So all these can take some actions from the action can be generated from this nearest fog node, can be from the aggregated fog node, or even can be from the cloud itself, depending upon where the application is being executed. So this is basically our model which we do have, let's say, designed. In grouping, why only 3? We did this, and this has been decided based on the clustering approach that we have done. Why only these 3 kind of so we did this particular analysis, and I'll show you the data depending upon which these 3 types of clustering has been done. So clustering suggests that the 3 kind of clusters of the resources can be done. One is the fog node, another is the aggregated fog node, and third one is the cloud node. So a fog node where the response time in millisecond, aggregated fog node response time and duration may be short, but not in milliseconds, may go to seconds also sometimes. Cloud node are those nodes where we process usually the delay tolerant jobs, sometimes the low priority jobs, or sometimes even with the pricing also, if it has been mentioned in maybe the service level agreement also. Maybe processing on the fog node is a little costlier than processing on the cloud node. So that also aspect may be taken into the consideration, right? So this is how the classification of the computing nodes have been done. Then our admission control manager factually categorizes the request into these 3 categories depending upon the clusters of the computing nodes. So we do have the time sensitive and high scheduling class gets the first priority, application with some tolerance given the next priority, and delay tolerant or application with long-term storage are given the least priority or the lowest priority. And factually these are sent to the nearest node, fog node. These are for the aggregated fog node, and these kind of applications which are usually the delay tolerant applications. We say that they are given to the cloud for the processing purposes. If you will make a comparative analysis of the computing nodes, you can just make it out. Response time in millisecond in the fog node, seconds to minutes, minutes to hour. This is data storage is transient. Data to be stored is the transient because the memory is very limited in the fog node. Shorter duration. Here you can even the permanent storage also can be done at the cloud node. Geographical proximity is very local but wider, and it is a global. The cloud node are global. Applications, some of the applications probably which can be processed at the cloud node is healthcare robotics, medical localization, drone operations, critical industrial control systems, quick financial transaction, etc. Here, aggregated fog node, we can chat, SMS delivery, machine to machine communication, FTP, data visualization, all these may be given to the aggregated fog node. And here, heavy application, big data analytics jobs obviously can be given to the cloud node. The whole process of the model which has been proposed is like this. We do have unlabeled data. The total Google trace is unlabeled. We do the pre-processing and curating the data, as I told you. Then thereafter we applied the clustering. So clustering is able to classify this data into 3, and thereafter we are able to label some of the data. And thereafter we apply the classification algorithm so that the machine is trained. And the performance evaluation is done thereafter in taking the unlabeled data, where the accuracy, execution time, variability in accuracy, variability in execution time has been measured. Obviously, the best model which we have selected, decision tree, taken up there. Thereafter, all this data, the new sample data, which is normally the unlabeled data, is used, and the computing node is assigned to that particular data. This is mainly the model, the proposed model that we do have developed. We do have applied a variant of decision tree classifier, introduced various noise levels. K-mean clustering, as I told you, has been used to train and test the classifier. 3 batches of jobs have been considered, right? While applying the clustering, the figure or this particular picture denotes that what type of CPU requirement is there, what type of storage requirement is there, and we are able to find it out that normally the applications or the data, they are clustered into these 3 kind of things. These 3 clusters they usually form. One is cluster 1, which has been represented in green color. They actually represent the cluster which is most suitable to be processed at the fog node. Then we do have the next cluster represented in blue color, which is cluster 0. They are normally those kind of application along with the data which is to be processed at the aggregated fog node. And this is the cluster which is normally suitable for processing at the cloud node, right? And this led us to designing or defining the architecture of the fog integrated cloud in 3 clusters. Not only the data, the 3 numerical data which we have used, rather we applied the 2 nominal data also in terms of the priority, in terms of the time sensitivity of the data. Thereafter also we are able to find only 3 clusters. So we decided to make it on 3 clusters. The cluster 1 green referred as the fog node, the cluster 0 which is a blue for the aggregated fog node, and cluster 2 which is the red one is for the cloud node. Of course, we find some overlapping or the borderline data also, and that is what we thought of introducing some noisy part in the testing purposes also. So we do find some overlapping data which we considered as the noisy part of the data, and that is what led us to introduce some noise in the data also. For comparative analysis, we use total 9 classifiers along with our the decision tree classifier. All these classifiers have acted accordingly on the evaluation parameters such as noise sensitivity, time consumption, and so on. Decision tree, I mean, some of the observation that we were able to make it. Decision tree, logistic regression, and general linear model have fast prediction speed and accurate also with some noise sensitivity. Support vector machine is very accurate in terms of prediction but sensitive to noise. This DL and ANN predict well but takes time to learn. This deep learning and the artificial neural, that is what I told you in the beginning itself. They are too heavier, so it makes them difficult to be implemented at the fog node. So DL and ANN predict well, but takes time to learn the input data pattern. As far as other models are concerned, like the GBT, SBM, and GBT, they are also good from accuracy perspective, but the interpretability lacks in the runner-up list. So ultimately, we came up with the decision tree classifier in implementing this particular model. The evaluation process has been divided into two parts. First part focuses on the result in terms of accuracy and time execution. Second part focuses on the test of significance of the result using the standard statistical performance measure. So we do have introduced some attribute noise also into the data set, which enables the data set to classify, to deal with the problem of the overfitting. That we were able to corrupt each a different portion of the sample were selected. Noise as a different percentage of novel data value, noise data value has been introduced. Like we added 5% noise, 10% noise, and 20%. The percentage of noisy data is further divided into two parts for each class, and each class have equal sub percentage of error populated across the data. The percentage of noisy data applies in each of the batch size, and each batch has equal number of distribution of noisy data. These are some of the measures that we do have taken in testing the model. The validation of the classifier is determined by means of a standard deviation. However, we have used 5-fold cross validation with the same result, but using a standard deviation, a range of result is obtained with plus minus of the change in actual mean result. Standard deviation gives us the result of 50 runs per data set with various levels of noise for each of the batches that we do have performed. And here comes the result where you will find for the batch 1. So this is the result of the batch 1 for the accuracy purposes of the different classifiers. Of course, the clustering is same for all classifiers, but thereafter we do have applied it for the different classifiers. And you will find that the accuracy, ours is a blue one. So sometimes you will find some are above the blue, but as I told you, they are too heavier to be applied in the fog integrated cloud environment. So accuracy has been represented here for the batch 1 on the different noise levels, 5%, 10%, and 20%. Similarly, the execution time also. As far as the execution time is concerned, you see the blue line, which is the decision tree classifier, which always says that the decision tree classifier from the execution time point of view is the best for the batch 1. Almost the same result is obtained with the batch 2 also, where we have almost 700 jobs, 700 applications for execution. So you see that this is the result for the accuracy. This is the result for the execution time, and this is for the batch 3. So you see that batch 1, batch 2, batch 3 also almost have the similar kind of a pattern in the result from the accuracy point of view as well as from the execution time point of view. If you altogether consider the algorithms from depending upon the batch size altogether, the change of accuracy in standard deviation, it comes like this for the batch size 1, batch size 2, and batch size 3. Similarly, the variation in time execution in the standard deviation, it comes like this. So, and final comparative analysis can be made this way. So, decision tree comes to be the prediction speed is fast, memory usage is low, training time is low, dispersion inaccuracy is low. You'll find sometimes some other like GLM also fast, logistic regression also fast in prediction, but probably they are not good in other attributes if you look into these other classifiers. I hope that I'm able to make it out the different type of classifiers, and we conclude that decision tree works very well in this particular model. So it's a kind of a hybrid model for intelligent admission controller, where the clustering followed by the classification has been done. From accuracy as well as from the efficiency point of view, the model seems to be very fit to be executed on the Frog integrated cloud environment. And of course, we tested it on the Google Trace. We are able to get the good result, and hopefully, think that this particular model will serve the purpose well. I think that's enough. That's all from my side. Thank you very much for your patience hearing. And now, if you have any questions, probably you can forward it to me. Thank you.
Yes, sir. There are two questions from the participant side. One is from Ashok Kumar. And similar question is asked by the Asmita Jagtap is there any real-time application of fog computing used in current industry? Or similarly, Asmita has asked a real-time application of the cloud computing or etc.
I already have listed in one of the slide the kind of applications that the fog can serve, right? Right, like we said that the time-sensitive applications, usually, which we call as the real-time applications, like the health domain, right? We require to process the data as soon as possible in the health domain, right? So we have the fog nodes available to us, so that the data can be processed at the fog node rather than sending it to the cloud. Because I already told you, sending it to the cloud and coming back from the cloud after the processing may involve some network delay. So you see that we can serve the same purpose executing it on the fog node itself. So the kind of applications has already been listed here, listed there in one of the slides. So I think you can, if you see that, if you say that I'll go through the slide, that particular slide, and can mention many of the applications like drone applications, the health informatics, and many other real-time applications. The fog serves the purpose well, right? Any other question?
One question is asked by Ashish Ranjan Mishra, sir. What is present work in area healthcare with help of fog computing and IoT?
What is present area of work?
What is present? Yes, the same. Yes, sir. What is, although he written what is present work in area of healthcare which uses fog computing and IoT?
Many health domains are using the fog computing, right? The whole health informatics is based on the fog computing, rather fog integrated cloud, I'll say, because they do take some historical analysis also. They do consume some historical data also. So let's say the ailing person will generate the data immediately, which can go to the fog. But then probably the other data also can be retrieved from the cloud, which we call as the historical data. If some long-term processing is to be done, the all amount of the data can be sent to the cloud for the processing purposes. But let's say if some immediate action is required, then probably this can be done, this can be processed at the fog node itself. So lot of health informatics is based on the fog computing itself, fog domain itself. And fog along with the cloud serves the purpose well, right? So fog cannot be seen in isolation with the cloud. Fog has to be seen in complementation with the cloud computing, fog and cloud together, right? That is why we call it as a fog integrated cloud. Okay.
So thank you, sir, for giving such a nice presentation and elaborating this lecture on resource provisioning in fog integrated things. We are thankful to you, sir, that you have accepted our invitation and given such a nice lecture. Many people are responding that this is a great session, such as Professor, I think one professor is Subham, Professor. We are getting several responses of sir, this session, that very great session. Thank you, sir. Thank you.
So yeah, so thanks a lot for your patience hearing. Almost more than 1.5 hours you stayed with me and you gave a patience hearing. I hope that this particular session, the work that I presented may help you in designing your own algorithm in the future. So thanks a lot. Thanks, Pawan. Thanks, everybody. Thanks, all the participants. Thank you very much. Namaskar.
Well, thank you, sir.
So dear participants. Okay, I'm leaving. Pawan, I'm leaving. Okay.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Thank you. Thanks a lot.
So, dear participants, the next session link has been sent to your mail ID. And please note that it will be started in just 4 or 5 minutes. We have given the time 12:15, but since it is finished just at 12:15, so it will take 2-3 minutes. And one thing everybody should note that no entry will be allowed after 15 minutes. As AICT has it is mandatory instruction in AICT that 80% attendance is mandatory. So after 15 minutes, it will not be allowed. And second important thing, please note that we will put the attendance link randomly in between the session, and it will be active only for 15 minutes. So those who will not be in that time, that will be marked absent. Since it is we are using Google Meet on private domain, so it is possible that automatic recording is not being done or anything else, because more than 100 participant has been allowed. So it was not supported by the institute mail ID. So I have taken a different domain and bought it. So their business module, so said they have said that it is not yet incorporated. Although we have downloaded some tool, but yet it has to be verified. So please ensure your attendance on the Google link which we provide, and it will be active just for 15 minutes. Once it is provided, suppose second session will start 12:15 and we will provide it suppose 12:30, then it will be only active up to 12:45. Okay, so with these and also it is requested to all of you that please unmute your video and microphone, so that I am not forced to remove anybody, because if it is in fact it is not disturbing if you on your video, but it is the just a kind of instruction, because once somebody is doing something, or suppose somebody is so it is not good to not follow the instructions. All of you are faculty members, so you follow, you know all these rules and regulations, how to deal such a big platform where over more than 200 participants are attending. So please, please follow these rules. Thank you. We will we have just started next session. Please leave this and start new session. It is more than 30 have joined. Please join next. Please leave this one and join next session. Thank you. Please leave this session and. Yes, we will see if somebody has joined and it has been dropped for 5 minutes. We will rejoin. We will admit them. But anybody who is new entrant, actually we are seeing 2-3 people are monitoring. So it will be cleared in till tomorrow. It will be cleared. Today I am admitting all one. Just I am giving instruction that what will be done from tomorrow onwards. Okay. So one participant has asked this, so just I have replied. Please leave this immediately and join next session. Still there are 40 participants. So because next session is about to start in 1 minute. It is on your mail ID. Link has been sent on your mail ID. Please join. Next. So just still there are 33 people, but I am terminating this session. Again, requested to you that please join next session through another link which is sent on your mail. Thank you. Stop again.